Bismillahir Rahmanir Rahim. This is lecture 6 in the course Electronics Devices and Circuit. So this time it's again diode, but this time we will try to differentiate the diodes different models. Number first model is ideal model, and then the approximate, and then third is the practical model. So in the previous lecture, we studied about the diode, and we studied something about the ideal diode. But this time we will study again the ideal diode in comparison with the approximate diode model and in comparison with the practical diode model. So please remember, as maybe I have said before, these characteristics are not going to be useful only for the diodes, but it can be useful for the next devices, electronic devices. For example, the transistors, the MOSFET, the FETs, the TIC, DIC, SAR. I mean, this can be applied to many other devices, because every time if you are introduced with a new device, you should be able to describe, you should be able to clearly understand what is the ideal model of that device, the approximate and the practical model. So this is not only going to be useful for the diode while you study the diode, but it can be useful for the number of other new devices. As after this device, we will start to move towards the transistor and the MOSFET. So please remember, this can be useful. So please try to understand now. This is the basic level of the diode is the basic level that provides you the basic understanding of the three models. So please go through this lecture, the PDF and the textbook, and then try and grasp a very strong knowledge, clear and transparent knowledge. We start again. So this is the ideal versus practical diode. We already have seen before the ideal diode, and we know that for the ideal diode there is practically, and for the ideal diode there is no avalanche breakdown, there is no barrier voltage. So if you want to turn on the device, you slightly apply a positive voltage, then it will turn on at any positive voltage. And if you apply a negative voltage, it will remain turn off for any negative voltage, and there is no breakdown, there is no there is no PN junction barrier. So this was the ideal diode we studied somewhat before, but this time we will study ideal diode in a circuit. As before, we just stated using the PN junction, but this time we will try to understand these three categories, these three models of the diode in a circuit. So I have shown here a circuit. It has three components. The supply voltage, it could be plus 12 volt, a battery supply voltage, or any regulated or unregulated DC voltage. And it has second component is the diode, because this diode we have to turn on and turn off, so we need this diode. And there is a resistor. So this is the resistor circuit, and we have to understand why this resistor here. Let's suppose if we don't place, this is the important understanding, because this is the first circuit, so we will try to elaborate it more and more. So for example, why this circuit, why this resistor here? Let's suppose if we don't place a resistor and we make a direct connection from battery to the positive terminal, what will happen? So now this time, of course, the plus is directly connected to the anode, and the cathode is the negative terminal of the supply is directly connected with the cathode. So immediately, the supply is connected. Immediately, the diode will be turned on. And what is the ideal status of the turn on? It's a short circuit. So it will behave as a short circuit. What is happening now? This plus terminal, if it is a plus 12-volt battery supply, then what we are doing here, the plus terminal is we are wiring directly connecting with the minus terminal, so there will be a blast. There can be there the damage. The battery will definitely be damaged, or the wires or the other things will burn out immediately, and this is never allowed to do. So that is why we place a resistor always. For example, if the diode is on, so we don't have a direct connection. We have a barrier. We have a resistor here. So the current through the battery can be controlled by this resistor. So this resistor is used to limit the current. It does not allow the short circuit of the supply in case the diode is turned on. So please remember, we always need the circuit. We always need this resistor for the analysis purpose. Okay, but in practical, we don't use the resistor normally. We use load. For example, it can be a bulb, it can be a lamp, it can be actuator, it can be DC motor. So it can be anything. So we in practical circuit we don't use this one, but this is for the sake of simplicity. We put just a simple resistor, and then we try to analyze the circuit. So in actual, we instead of resistor we use this is, I think it's this one is a 12 volt 12 volt DC LED. So or the lamp. So when this plus is connected with the plus of the lamp, and the minus is connected with this one, and whenever the diode is turned on, the lamp will turn on. The maximum the current will flow through the light, through the lamp, through this LED lamp, or whatsoever is this one. So the device will turn on. Okay. Okay, so it can be anything, any load. Normally it is load. It is whenever it is not resistor, but for the academic purpose, for the understanding, for the analysis, basic simple analysis, we use the resistor. So this is why it is here. Hope you understand why there is a need of this resistor. So okay, when the diode is turned on, so the current will flow. Now we want to know what is the current. So this is the diode, and we are drawing still the ideal diode. So for the ideal diode, diode forward bias means switch is closed. So diode forward means is ideal switch, so switch is closed. This one is like a conductor, like a copper wire is connected from here to here. So what will be the resistance? The resistance will be 0. Okay, and how we can calculate the so this is the current. We want to calculate the current depends on the value of the resistance and the voltage. Okay, supply voltage. So the if is basically Ohm's law. I is equal to V upon R. So V is the voltage. We are calculating the voltage, the current through this resistor, current through this resistor. So the resistor has this resistor has voltage. This terminal is connected with the minus supply, and the other terminal of the resistor is connected with the plus supply. So it means the voltage across this resistor is Vs, the supply voltage. And what is the resistance? In this loop, there are two component, resistor and the diode. So the resistor of resistance value is R, and this resistance, because it's a short circuit, so its resistance is taken as 0. So we can calculate for the forward bias the IF current. So now take for the reverse bias. For the reverse bias, we know that for the reverse bias, minus is connected to the anode, plus is connected to the cathode. So it is reverse bias. The current through will, because we are still at understanding ideal diode, the current through will be 0, and the equivalent model shows that if the current is 0, this means diode is off. Diode is off means it looks like this one, and the current through this will be uh, so the calculation is this one. This current can be calculated by the supply voltage and divided by this resistor R, plus the resistance of this diode, and the resistance of this diode is open circuit, so it will be infinite. So this is the reverse bias condition. So mechanical switch is bidirectional. but diode is unidirectional only. As we discussed before in the first point, that ideal property of a diode can be discussed by using a mechanical switch, but we cannot say the ideal property of a diode is equivalent to the mechanical switch, to the mechanical switch. That's going to be correct. That's going to be incorrect. So that's why we can say, okay, we just want to take the example of a mechanical switch, so we can correlate with the diode as a switch. So in this case, it says that mechanical switch is bidirectional, but diode is unidirectional. So this is the difference between the mechanical switch and the diode. The mechanical switch, if this point is connected with the plus supply and this point is connected with the minus supply, so the current will flow from plus to minus in this direction. Okay, so the current will be from left to right. If taken another example where this one is connected with the minus of the supply and this point is connected with the plus of the supply, whenever this will turn on, the current will flow from plus to minus. So current will flow from right to left. So in the mechanical switch or the electrical switch, this is bidirectional. Current can flow from here to here and current can flow from here to here, but this is not true for the diode, for this semiconductor diode. In the semiconductor diode, the current will only flow when the anode is positive and the cathode is negatively connected with the supply. So the current direction is always this one. The current can never flow from from right to left, from anode to cathode. Yes, it can never flow. So this is only unidirectional device. Current can only flow from the higher potential to the lower potential. That is the conclusion. So now in terms of the voltage, VI characteristic of this diode, the forward, it says that if we apply a little positive voltage, then the maximum current will start to flow. So this is the forward bias region. Whatever be the positive voltage, if it is positive voltage, then the current will be maximum. If the voltage is on the left side, that means if the voltage is negative for this entire negative range of the voltage, the diodes will turn off. It will be in reverse bias region. In conclusion, we can say for the positive voltage or the entire positive voltage, the current will be maximum, and for the entire negative voltage, the current will be zero, and it is in reverse bias. So we can see a little, it is not here, we are not waiting for 0.7 volt, because in ideal diode we are assuming there is no barrier voltage, so there is no need to wait for 0.7 voltage for the silicon case. Hope you understand. Now the time is to understand the approximate diode model. For the approximate diode model, we are in continuation with the ideal diode model. We will try to understand that when we know that for the ideal diode, if turns on, it allows flow of maximum current, and Vd is equal to 0 volt. If it is off, it block all current, and Id is equal to 0. So on period maximum current, off period current is 0. For some of the applications where high voltage and high, okay, so the question is that if this is the ideal model, where we use this ideal model? We normally use the ideal model of the diode whenever there is a high voltage in the circuit or there is a high current. Excuse me. Yes. So, for example, if we are using a power diode and it is handling 100 volt or 1000 volt, so it means the 0.7, that is the barrier voltage, is negligible here. So although the diode has barrier voltage, but if the diode is going to apply in a circuit where the supply voltage is more than 100 volt or 1000 volt, then the consideration of this 0.7 volt is negligible. So we ignore this 0.77 barrier voltage. For similarly, for the current is also true. If we are having a very high current, then the leakage current is in the range of the milliampere or the microampere. So this leakage current can also be negligible. So simple is the ideal model is also useful for some of the applications where high voltage and or high current is required. Usually the diode is considered as an ideal diode, and simple analysis is done for the sake of simplicity. Hope you understand. But it is not always true that we should use the ideal property. For example, if the voltage is very low, so for example, if the supply we are using is having 1 or 2 volt, and then we cannot ignore the uh, diode barrier voltage of 0.7, because if the supply is 1 volt, then the diode voltage is 0.7 volt. That is comparably, that is both are comparable. This 0.7 cannot be a negligible value. So for the cases where the low voltage or the low current is analyzed, or the for example small signal analysis in the signal processing, so we cannot use this ideal diode. However, for many of the applications analyzing the circuit, considering diode as an ideal diode is not accepted. For such cases, an approximate diode model is used. And this is the approximate diode model. Here we can say this, and this looks same, except that this plot is moved rightward in order to point out the 0.7 volt. So this shows that the diode will turn on at 0.7 or beyond 0.7. For this value, the diode will have a sharp current. That means infinite amount of current can pass through the diode because it has 0 ohm. And before 0.7 and towards the right side, even it can be in minus, then the diode current is 0. We can see the diode current is 0. So this is the approximate model. It looks like the approximate model and the ideal model are almost same. Yes, that is true, but it includes the barrier voltage in the circuit. Okay, and this is the 0 ohm. Yes, so for the approximate model, the 0.7 is the threshold voltage. We have to take in consideration this voltage while the calculation, and we can also assume here the diode resistance is 0 ohm. However, for many of the applications analyzing the circuit, considering diode as ideal is not accepted. For such cases, an approximate model diode is used. This is the approximate model diode. For this approximate model, it is assumed that diode remains on after 0.7 volt, otherwise it remains off. So after 0.7, this is the on period, and the rest of the voltage is for the off. The more accurate analysis, yes, this looks like this is slightly different, but this is not the exact and the true characteristic curve of the diode. So for the cases where you want to have a very accurate analysis, you should need to calculate very carefully, and because you are doing some design work, some research work, or some maybe you are doing some manufacturing work. So you want to have to very accuracy you want to have. So under such conditions, neither this will be used nor this will be used, but we will use the practical diode, the diode which we have in our hand, and we will draw the characteristic curve, vi characteristic curve for this diode, or we can take that characteristic curve from the manufacturer manual. Okay, so for the this is the real diode or the practical diode. So it has different regions. It means forward region, knee, the voltage from 0 to knee, and knee to forward region, and then we have reverse region, and we have avalanche breakdown. It looks like this is quite different from this one and this one. Yes, it should be, because this is real diode. This has no assumption. This has no exemption. This has no voltage, and the current is considered negligible here. So how we can define the simple way, what I can say, if you look here, At 0.7 the current is maximum, but if I ask you at 0.5 what is the current? Current is 0. At 0.2 what is the current? Current is again 0. At 0.1 just at 0.6, 0.5, all these voltage values has corresponding current values equals to 0. Okay, but this is not true here in the real. If you start from axis, positive axis, and if you say from okay this is 0, and then you proceed towards the right hand side, it can be 0.1, 0.2, 0.3. So you can see at each DC voltage, at each voltage point there is a corresponding small current. If you touch to the 0.7 volt here, then we can say okay this is also a small current. But the truth is that at every voltage point there is a corresponding current. So if you go beyond 0.7 volt, so it starts the ramp is changed, ramp is very fast, and for example 0.7, 0.8, 0.9, 1 volt, it has sharp increase in the current. So we can say, simple statement for the practical diode, we can say that at each voltage point there is a corresponding current, no negligible. Okay, although from 0 axis to 0.7 new voltage there is a small rise in the current, but after new voltage there is a high rise in the current. So there is low current flow and there is a high current flow. So even this is true for the negative voltage. If we say that okay the voltage is negative, so at every point of the negative voltage there is a corresponding current, there is a corresponding microampere current. This is milliampere current scale, and this is microampere current. So there is always a microampere current. So the analysis where we take consideration of current for each voltage point, and then we make the characteristic of this is known as the practical diode. Hope you understand. So simply the practical diode has from 0 to this knee voltage has slow has very low current, but after knee it's a high current. And we can also see here that this is also true for the negative voltage, and there is also avalanche breakdown. Okay, let's talk about the second property of these practical diode. Here we can say that the average resistance is 0 ohm. Why the average resistance is 0 ohm? But we cannot say that the average resistance of this for the practical diode is 0 at any value. It will have some value. So how we can say understand this a little bit more? For example, while calculating the resistance of this, we can apply the Ohm's law, and in according to the Ohm's law, resistance is equal to voltage divided by ampere. So what at 0.7, at this point the voltage is 0.7, and at this point the current is non-stopping. It allows infinite amount of the current to the diode. So the current is infinite. It has a capability to allow infinite amount of current. So it is infinite. So every resistance will equal to 0 ohm. So this is the 0 ohm. We can just as per visual understanding, we can say that if the current is right angle triangle, so is the plot is right angle triangle is straightforward, so its resistance will be 0. Okay, but in this case if you see here, okay, now take another example. For example, here the voltage taken is 0.3. So this is 0.7, might be this is 0.5, maybe it is this one 0.3. So at this point what you can see, the voltage is, yes, voltage is 0.3, and the current through at this point is 0. There is no flow of current on vertical. It is exactly at 0 level. So the voltage will be, the current flow will be 0. So what will be the resistance? So it will be infinite. So conclusion is that for the ideal and the approximate diode, we have two resistance. If it is on, the resistance is 0. If it remains off for this entire period, for this entire duration of the scale, then the resistance will be infinite. It means it will remain completely off, and here it will remain ideally on, completely on. But this is not true for the practical diode, as if we have 0.3 volt, we have some current. We have 0.7 volt, we have some current. If we have 0.8, so maybe we have this amount of current. At 0.9 we have, so at every point the current changes, so it means at every point the resistance will also change, and the resistance cannot be 0 or the infinite, at least for this period, for this normal operation. So there will always be resistance, but what we understand, because here from 0 to ni, the flow of the current is very low, we can say okay, the resistance might be very high. That's true. And after this one, the ramp is more vertical, so we can say okay, the flow of the current is higher than before, so we can say the flow of the current is higher, then we can say okay, the resistance is low. Okay. So let's just describe some practical. See, for the practical diode, at every diode voltage, there is a change in the diode current. The practical diode analysis adopts the Shockley equation. Yes. So if diode is provided greater than 0 volt, then the diode is forward bias and current flow. We can say okay, the diode is in the forward bias and the current flow gradually it starts from very low value. Current starts from very low value from 0 to knee voltage. However, after crossing the new voltage, a heavy current flows, making the diode gradually forward bias. The forward bias ramp determines the average resistance. That's true. This ramp determines the average resistance. So more this is the vertical, it will be the resistance will be very low. Similarly, in the reverse bias, although diode, although we normally say that the diode is reverse bias and it is off, but it keeps flowing the reverse saturation current. This is in the range of the microampere, we can say. The practical diode properties, the practical diode, if forward bias exhibits, it can be greater than 0.7 volt or equal to 0.7 volt, and when it is forward bias, we can say that it has 0.7 or greater than 0.7, and we can draw its equivalent circuit. This diode can be replaced as a barrier voltage, as so we must have to, the supply should be capable to overcome this barrier voltage. So this can be 0.7 or more than 0.7. And the calculation, we can use the Kirchhoff's voltage law. So the supply voltage is going to distribute it among these two components, this one and this one. Supply voltage, the supply voltage is equal to the voltage across the resistor and the voltage across the diode. So this supply voltage equal to resistor, the voltage across the resistor is basically current multiplied by the R as per Ohm's law, and this diode voltage is replaced by forward voltage, because forward voltage can be 0.7, 0.8, 0.9. It depends on the operating point where it is being operated. So the IF is equal to, here we calculated the IF is equal to the flow, the IF current is basically the current through the through this resistor or through this device. Because both are in series, the current will be same for both of the component. Let's assume we can calculate the current through this resistor. If we want to calculate the current through this resistor, then we want to know its potential difference. Its potential difference is here, it is Vs, and here it is diode voltage. So we must have to, this voltage, we must have to use this Vs minus Vf. So this voltage is going to distribute among this one plus this one. So if we want to know the voltage difference across here, we will subtract this voltage from Vs. So Vs minus Vf. Hope you understand this one. These are the basic from the elementary school or the college level. You must have understand. You must have studied the Ohm's law. So this was the forward bias, and the practical model forward bias. And remember, in the practical model of the forward bias is not always 0.7 volt, it can change. So for the reverse bias, we know the current is reverse because this is reverse bias. So here we can say that ideally it is disconnected, but it is not practically, it is not disconnected. So I just shown like this one. It looks like it is stopped. So this one has voltage -1 minus, and this one has voltage plus. So this diode voltage will equal to the V, and the because this is practical diode, there is always a leakage current, and leakage current is the conventional leakage current will always flow from plus to minus. So this is in opposite to the forward current. So the leakage current and the diode will have this leakage current reverse bias. What is the voltage across the diode if forward bias? The voltage across the diode, when it is forward bias, it can be calculated by its VI characteristic curve. Okay, so where is, and what is the voltage across the diode if reverse bias? If it is reverse bias, its voltage can also be calculated by the its VI characteristic curve. So this is the VI characteristic curve. We can say that it has the voltage at every point has current, corresponding current. So this is the characteristic curve. So in summary, important conclusions and concept: do it yourself from the textbook. So somewhat we described here about this topic, the diode, ideal, real, practical, approximate. So this topic you have to cover from the textbook yourself. Okay, okay, class is over. Thank you very much. Take care. Allah Hafiz.